Hey folks, in section 3.1 we're going to take a look at derivatives of constants, powers, and sums. And really what this is all about is it's going to give us some shortcuts, if you will, on how to compute derivatives. So the objectives we're going to look at here in section 3.1, the first one is going to be the derivative of a constant. So we're going to see a shortcut, a formula, a rule, if you will, on how to compute the derivative of a constant. The second objective we're going to look at is how can we determine the derivative of a power function. Going to really like that little shortcut rule. The third objective, we're going to look at how to differentiate a function that is multiplied by a constant. That'll give rise to a rule that's called the constant multiple rule. The fourth objective is how we're going to differentiate the sum and or difference of functions. So if we have a function that's composed of the sum or difference of other functions, we're going to come up with a little rule on how to compute its derivative. And then finally, the fifth objective that we'll look at here in section 3.1 is applying the differentiation rules to some applications. So here we go. First off, for a function y equals f of x, the following can be used at any time to represent the derivative. F prime of x, that's probably the most popular. Y prime, if my function is of the form y equals something, I could represent the derivative with y prime. Or if it's y equals, I could represent the derivative with dy dx. The last one there that I have listed, d dx of f of x, I'll probably only use that to communicate if I want you to get the derivative of a function. In other words, if I have a function and rather than write down, determine the derivative for this function, I may just write down d dx and then in brackets whatever the function is. So I kind of save that last one more for telling you the operation of getting the derivative. All right, so here we go. First rule, the constant function rule. For any constant k, so that's any real number k that you can think of, if your function is the form f of x equals k, then the derivative, f prime of x, is 0. In other words, the derivative of a constant is 0. Very friendly little rule. The derivative of a constant is 0. And here in the first example, we're going to differentiate the following. F of x equals 12, and in part B, g of x equals 5 times the 6th root of 4. So at this time, I'm going to head off to the chalkboard and work out the solution to this example. Hey folks, we're making our way through section 3.1, looking at some rules or shortcuts of computing derivatives. And the first example was right after we were just talking about the constant rule. It says the derivative of a constant is 0. And this was the first example. This is where we left off. Was differentiate the function part A, f of x equals 12, and part B, g of x equals 5 times the 6th root of 4. In both parts, this is so friendly, 12 is a constant. So the derivative is 0. So for part A, derivative is 0. Part B, I have no idea what the 6th root of 4 is, nor do I care what it is. I just know that it's some number. It's a constant. 5 times that constant is still a constant. Derivative of a constant is 0. So part B, we have g prime of x is equal to 0. So the very first rule or shortcut we have is a very friendly one. The derivative of a constant is 0. Now let's head on back and try to learn, let's look at some more shortcuts or rules for computing derivatives. All right, now that we did that example, see, I told you you'd like that rule. It's pretty friendly. Continuing on, anytime you have a function of the form f of x equals x to the n, and n is just any real number you can think of. A function of the form f of x equals x to the n, well, it's called a power function. And with our next rule for computing derivatives is called the power rule. And the power rule simply says if your function is x to the n, where n is any real number, then the derivative, f prime of x, equals n times x to the n minus 1. All right, in other words, it looks like what's happening if you have a power function, x to the n, to get the derivative, the exponent is just coming out front as a multiplier, and then we subtract 1 from the exponent. That's what it looks like. Pretty friendly rule, but at the same time, it's pretty powerful. No pun intended. So this example here, we're going to differentiate the following functions, and there are 3 of them. Part A, f of x equals x cubed. Part B, g of x equals x to the 8.57. And then part C, h of x equals 1 over the cube root of x. So if you need to, write those down, because at this time, I'm going to head off to the chalkboard and do this example. All right, the next rule we just discussed was called the power rule, and I thought I'd write the power rule up here. If your function f of x is x to the n, and I didn't write everything up there, but n is a real number, then the derivative, f prime of x, is equal to n times x to the n minus 1. I know mentally the mechanics that we're kind of thinking here is, well, whatever that exponent is, it comes out front as a multiplier, and then you subtract 1 from the exponent. And that's how you use the power rule to get the derivative. So the example that we just left with was to differentiate, and there were 3 parts, an a, a b, and a c. The function in a was f of x equals x cubed. We're going to get the derivative of that. Part b, get the derivative of g of x equals x to the 8.57. And then in part c, get the derivative of h of x equals 1 over the cube root of x. And what I do is I just work out parts A, B, and C. I'll work them out here. I'll have to do some erasing, but that's no big deal. So here we are, performing the mathematics on doing part A. Your function is x cubed. Function is x cubed. Use the power rule. So when we use the power rule to get the derivative, f prime of x, the 3 comes out front as a multiplier. That's using the power rule. X, and the power rule says now subtract 1 from the exponent. So we subtract 1 from the exponent. 3 minus 1 is 2. And that's all there is to it. That is the derivative of x cubed. It's a lot more efficient, a little quicker than using that definition of the derivative that we talked about in the last chapter. But that's it. Boom. We have the derivative. So let me grab my eraser so we can do part B. So part B, let's see, the function is g of x equals x to the 8.57. No big deal. It doesn't matter that this exponent is an ugly looking number. It's a decimal, 8.57. It's no big deal. It's still a real number, which means we go ahead and we use the power rule. Use the power rule to get the derivative. So we use the power rule. 8.57 comes in front as a multiplier. And then we just subtract 1 from the exponent. So 8.57 minus 1, that is a 7.57. And that's it. That's the derivative for part B. So let me grab the eraser again so we can do part C. And there's going to be just a little bit more work here in part C. Because part C, the function I'm given, h of x equals 1 over the cube root of x. Okay, I have to remember some rules of, some old rules in algebra, old rules of exponents. The first rule that I have to remember is that a cube root can be rewritten as an exponent. So I can rewrite the denominator, that cube root of x, I can rewrite that as x to the 1/3. So I had to, my first step here was algebra. Okay, next I need to remember another rule of exponents, which will allow me to rewrite this 1 over x to the 1/3 as x to the negative 1/3. So an old rule of exponents allowed me to go from here to here, and then another rule of exponents allowed me to rewrite this as x to the negative 1/3. So I did 2 steps so far, no calculus, it's just algebra. I've rewritten the function into a form where now I can get the derivative, very straightforward, very friendly. I can get the derivative using the power rule. So here we are getting the derivative using the power rule. H prime of x is, so I look at this, I use the power rule, I bring the negative 1/3 out front, and then I subtract 1 from the exponent, so negative 1/3 minus 1, that would be a negative 4/3. And then, let's say I just didn't want my final answer to have a negative exponent. I could simplify this to a negative 1 over 3x to the positive 4/3. So algebra was actually our friend here. Algebra allowed us to rewrite the function so we could then quickly get the derivative using the power rule. So I'll tell you what I'll do here real quick. I'm going to erase this. And I mentioned some of those rules of algebra. So let me just kind of write them down real quick. These are rules of algebra that you might find useful while we're doing calculus. The first rule of algebra that might be beneficial in doing derivatives is the nth root of x. That's what I used here to rewrite cube root of x as x to the 1/3. The nth root of x can be rewritten as x to the 1 over n. Another one is, well, let's say you had the nth root of x to the m. Well, you could rewrite that as x, and then the exponent would be m over n. And then finally, the other one that I used in there, in part C, x to the negative n. You can rewrite that as 1 over x to the n. So you can see these are like 3 quick rules of exponents that I know you've all seen in algebra. I thought I'd write them down for you real quick. I used this one in part C to rewrite cube root of x as x to the 1/3. And then I used this one here to rewrite that 1 over x to the 1/3 as x to the negative 1/3. And if I wanted to, I could use this rule to, in my answer, my derivative, to rewrite x to the 4/3 as the cube root of x to the 4th. I'm not going to. I'm just going to stop right there. Okay, here's what I'd like you to do right now. I'd like you to pause the video and go into the textbook, section 3.1, and try exercises 13 and 14 in section 3.1. So go ahead, pause the video, try these 2 exercises, and when you restart the video, I'll have the solution for those 2 exercises to make sure you did them correctly. So go ahead and pause the video and do those 2 exercises. Alright, hey, welcome back. Here I am going to work out numbers 13 and 14. In exercises 13 and 14, you were asked to get the derivatives of the functions. So in number 13, your function is x to the 6th. Thanks to the power rule, we simply can get the derivative to be 6x to the 5th. Power rule, 6 comes out front, subtract 1 from the exponent. That's it for number 13. In number 14, again, we're going to use the power rule. So the derivative, see the 10 comes out front, so that gives me 10x. Subtract 1 from the exponent, 9. That's the derivative for 14. So I hope you got numbers 13 and 14 correct. And that's a look at the power rule. Okay, we're going to head on back now and let's explore the next rule, which is called the constant multiple rule. All right, after doing that example, practicing the power rule, I hope that you also did, as I indicated, numbers 13 and 14, a couple of homework problems. And you're starting to get some comfort with the power rule. Next up, the next objective we're going to look at is the constant multiple rule. So here you go. This is a new rule. If your function f of x equals k times g of x, and k is any real number, so you have a real number times a function, then the derivative f prime of x equals k times g prime of x. So in other words, if your function f of x is a constant times a function, the derivative f prime of x is nothing more than the constant times whatever the derivative of whatever that function is. Okay, let's practice this new rule. So in this example, we're going to differentiate the following three functions. Part A, we're going to differentiate y equals 7x to the third. Part B, g of x equals 7 over x to the eighth. And part C, h of x equals 2x cubed over 5. So again, if you have to, go ahead and pause the video, write those down, because I'm going to head off to the chalkboard and work out the solution to this example. All right, we just looked at the constant multiple rule, and I thought I'd write down an abbreviated version of it. Constant multiple rule says if your function f of x is some constant times a function. You know, the constant k is a real number, and this function g is a differentiable function of x. But if your function is a constant times a function, then the derivative f prime of x is nothing more than k times g prime of x. So here we are, this example. You're asked to differentiate three parts. Part A, y equals 7x cubed. Part B, differentiate g of x equals 7 over x to the 8th. And then part C, differentiate h of x equals 2x cubed over 5. So let's work part A here. Get the derivative of the function 7, y equals 7x cubed. Well, there are two different things we could call the function here. We could either call the function y prime or the derivative. We could call the derivative y prime, or we could call the derivative dy dx. I don't care which you call the derivative, y prime or dy dx. I'm going to call it y prime. Okay, now since I have a constant 7 times a function, x cubed, I'm going to use the constant multiple rule. And here's what it would look like using the constant multiple rule. According to the constant multiple rule, the derivative is the constant, 7, times the derivative of that function. Well, we know how to get the derivative of x cubed. That's the power rule. So the derivative of x cubed is 3x squared. 3 comes out front, subtract 1 from the exponent. Cleaning it up, we know 7 times 3 is 21. So the derivative is y prime equals 21x squared. So this step right here is really what's happening with the constant multiple rule. The constant comes on down, and then you do the derivative of that function. That's what this line right here is showing you. In practice, what you're probably going to end up doing is you're going to end up going from here to here in one step. You're going to say, okay, I'm going to use the power rule and bring the 3 out front, and you'll say, well, 7 times 3 is 21, and then subtract 1 from the exponent and get the exponent of 2. Let's try part B. Let me grab my eraser. Part B, g of x equals 7 over x to the 8th. Our first step is to use some algebra. We have 7 over x to the 8th. So we need to rewrite this as 7x to the negative 8th. It's that rule of exponents that we just reviewed. So now to get the derivative, using the constant multiple rule, it'd be 7 times, so 7 times, now the derivative of x to the negative 8th. Well, the derivative of x to the negative 8th is negative 8x, subtract 1 from the exponent, negative ninth. Now we clean this up. We know 7 times negative 8 is negative 56. X to the negative ninth. And you know what? We could rewrite that without a negative exponent. Drop it back downstairs and get negative 56 over x to the ninth as the derivative. Now let's look at the next one, part C. Let's see what part C has in store. Grab the old eraser. Kind of erase this. So part C, your function is 2x cubed over 5. Okay, keep in mind this function is nothing more than the function 2/5 x cubed. So we can see it is a constant times a function. We're going to use the constant multiple rule. And when I use the constant multiple rule, yeah, I get a 2/5 times 3x squared. 2/5 times 3 is 6/5 x squared. So that's the derivative for part C. So that's a quick look here at 3 examples of doing the constant multiple rule. What I'd like you to do right now, I'd like you to pause the video, and in section 3.1, I would like you to try number 19 and number 23. So go ahead into the homework in section 3.1, try number 19 and 23, pause this video and do those 2. After you've done those 2, restart the video and I'll have a worked out solution for them. Alright, hey, let's see if you got 19 and 23 correct. So 19, you're asked to get the derivative of f of x equals negative 3 x to the negative 1/3. Constant multiple rule, so the derivative is a negative 3 times negative 1/3 x to the negative 4/3. Well, we know negative 3 times negative 1/3, that's positive 1. That's kind of cool. X to the negative 4/3, or I could write that as 1 over x to the positive 4/3. So that's it for number 19. Hopefully you got that. 23, again, the constant multiple rule. So the derivative is negative 2/5 times, now the derivative of that, so the derivative of that is 5/3 x, subtract 1 from the exponent, so that gives me a 2/3. Clean this up, negative 2/5 times 5/3, well that's a negative 2/3. So the derivative is negative 2/3 x to the 2/3. So hopefully you got 19, hopefully you got 23, and we're ready now to look at the next rule of computing derivatives. All right, so we just did the example of practicing the constant multiple rule. We also saw how some old rules of algebra can help make our life in calculus a lot better. So remembering some old rules of algebra. Hopefully you were able to do numbers 19 and 23 as I asked you to do. And I think we're ready to move on to objective 4, which is going to be the sum and difference rule. So this is our last rule of this section. So far, to recap, you've learned 4 rules. Rule 1 was the constant rule. The derivative of a constant is 0. Rule 2 was the power rule. Rule 3 was the constant multiple rule. And now here's rule 4, the sum and difference rule. The sum and difference rule just says if you have a function h of x and it's equal to f of x plus or minus g of x, and there could be more terms there, then the derivative, h prime of x, is equal to f prime of x plus or minus g prime of x. All right, hey, let's look at this a little bit. Let's look at this more in an English way. If you have a function h of x that's equal to the sum or difference of 2 or more functions, to get the derivative, you just do term by term differentiation. You do term by term differentiation. That's why it says f prime of x plus or minus g prime of x. And let's practice this now in this example. Here I have differentiate the following functions. Part A, we're going to differentiate the function 4x squared plus 7x minus 10. Part B will differentiate g of x equals 3/7 x to the 7th minus 4x squared. And then in part C, we'll differentiate h of x equals negative 5 square root x plus 7x to the negative 3/2 plus 8. So if you need to, write those down because it's time for me to head off to the chalkboard and work out the solution to this example. All right, hey, we just saw the sum and difference rule, and in short, what the sum and difference rule says is that if you have a function that's made up of the sum or difference of two or more functions, you can get its derivative by doing term-by-term differentiation. So here is the example. Part A, f of x is 4x squared plus 7x minus 10. To get its derivative, we just do term-by-term differentiation. So the first term is 4x squared. The derivative of the first term, 4x squared, is found using the constant multiple rule. So the 2 comes out front. 4 times 2 is 8. X to the first power. Move to the next term. Derivative of 7x. Well, that's just 7. Finally, the constant. We know the derivative of constant is 0. So that's it for part A. The derivative is 8x plus 7. Part B, sum and difference rule tells us to do term-by-term differentiation. So let's look at the first term here. Hey, we get to use the constant multiple rule again. So the 7 comes out front, 3/7 times 7. That's kind of cool. That just leaves us with the 3. X, subtract 1 from the exponent, which is 6. Constant multiple rule here on the second term gives us a minus 8x. So that's the derivative for part B. Now in part C, well folks, I need to do a little bit of algebra before I get started here. And specifically, I need to do a little bit of algebra on this pesky square root x. So let's rewrite that as negative 5x to the 1/2. And let me write down the rest of the function. Now let's do term-by-term differentiation to get the derivative. So the derivative of the first term, that's found using the constant multiple rule. So the 1/2 comes out front. Negative 5 times 1/2 is negative 5/2. X to the, subtract 1 from the exponent, so that's negative 1/2. Move to the next term, constant multiple rule. So negative 3 times 7, oh boy, I hate fractions. That's negative 21/2. X, subtract 1 from the exponent. See, negative 3/2 minus 1. That's a negative 5/2. And then the derivative of the constant is 0. And if you want to get rid of those negative exponents, you could simplify this to negative 5 over 2x to the positive 1/2 minus 21 over 2x to the positive 5/2. So that's it for this example. And in section 3.1, what I'd like you to do right now is I'd like you to try numbers 31 and 43. So I'd like you to pause the video, go to the section 3.1 homework, try numbers 31 and 43, and after you've done those, restart the video and we'll make sure that you have them correct. All right, hey, let's see if you got 31 and 43 correct. So number 31, the function was negative 5x cubed plus 7x minus 5. To get its derivative, using the sum and difference rule, I just do term-by-term differentiation. So the derivative of the first term is negative 15x squared, and the derivative of the second term is 7, and the derivative of the constant is 0. So there you go, number 31. Number 43 requires just a little bit of algebra to get started, so we can differentiate that pesky cube root of x. But folks, it's not that bad. You just rewrite cube root of x as x to the 1/3 power. And that little bit of algebra is going to make the calculus easy for us. So we get the derivative by taking the derivative of the first term. Well, that's a 1/3 x to the negative 1/3, plus the derivative of the second term is 2x, and then the derivative of the third term, using the constant multiple rule, we get minus 9x squared. And again, if you want to rewrite this without a negative exponent, you would have 1/3x to the positive 1/3 power plus 2x minus 9x squared. So I hope you got 31 and 43 correct. Now it's time for us to go check out an application. All right, hopefully you saw how friendly the sum and difference rule is, and you probably saw how the sum and difference rule incorporated a lot of these other rules that we've been dealing with, in particular the constant multiple rule. So I hope that you also did the exercises that I asked you to, numbers 31 and 43, and you got those correct. Now it's time to look at an application. So this is a real-world application. Let's see, here we have the number of hours of daylight in Joliet, Illinois during 2011 can be modeled by the function f of x equals negative 0.189x squared plus 2.505x plus 6.202. And here the independent variable x is between 1 and 12. That's our restricted domain. And x is the number of months since December 1st, 2010. And f of x is the number of hours of daylight. And we're going to do two things here. We're going to evaluate f of 4 and interpret, and we're going to evaluate f prime of 4 and interpret. And this is something we need to really get under control pretty quickly. It's going to be very common directions for quite a while, where we are going to evaluate and interpret, specifically the derivative, evaluate and interpret. So if you need to, right now, pause this video so you could write down the important parts of this example, because I'm getting ready to go off to the chalkboard to do it, and I'm not going to write all these words down again on the chalkboard. So if necessary, go ahead and pause the video, and then when you have it written down, go ahead and click play so you can watch the solution on the chalkboard. Okay, the example that we just saw of this function, it happens to model the number of hours of daylight in Joliet, Illinois during 2011. X represents the number of months since December 1st, 2010, and f of x is the number of hours of daylight. And then there were two things we were asked to do here. Evaluate f of 4 and interpret. Evaluate f prime of 4 and interpret. So let's start off with the f of 4. Okay, f of 4, you know to find f of 4, you're going to put 4 into the x's, and believe me, I am using my calculator to do this. And when I toss 4 in for all the x's, I get 13.198. You know, what does that mean? Well, x is the number of months since December 1st, 2010. So x has a value of 4, so let's count. For an x value of 1, that would be January 1st, 2011. 2 would be February 1st. 3, March 1st. 4 is April 1st. So this 4 is talking about April 1st, 2011. 2011. There were about 13.198 hours of daylight. Oops. In Joliet, Illinois, because f of x represented the number of hours of daylight. So the 4 tells us 4 months after December 1st, 2010. That's what tells us April 1st, 2011. And then the functional value, 13.198, that's telling us the number of hours of daylight. Now the second part, we're supposed to compute f prime of 4. Well, I can't do f prime of 4 unless I first determine f prime of x. So here's my function.
I'm going to get f prime of x by using the sum and difference rule and do term by term differentiation. So I differentiate the first term. So the 2 comes out front. Negative 0.189 times 2 is a negative 0.378 x, then subtract 1, so it's x to the first power. The derivative of the second term is just 2.505, and then check it out, the derivative of the constant, well, the derivative of the constant is 0. So now we need to evaluate the derivative. Now we can do the f prime of 4. Toss 4 in here for x, and again, I am going to use my calculator, and I get f prime of 4 to be pretty close to 0.993. All right, so now what does that mean? Well, we know 4 matches up or corresponds to April 1st, 2011. So that's how I'll start my interpretation. On April 1st, 2011, the number of hours of daylight in Joliet, Illinois, I'm not going to write that down, but it's in Joliet, Illinois. This is a positive number. Remember, derivative gives us an instantaneous rate of change. It's positive. So the number of hours of daylight was increasing. It's a rate of change, an instantaneous rate of change. I need to see that dynamic word. It was increasing. And then I'll say at a rate of 0.993. Now remember, folks, it's a rate. There's a rate here. Rates have units, like miles per hour, dollars per year. Units. Here it would be hours. So I'll write hours per month. Because f of x represented the number of hours of daylight. X was the number of months. So the units would be hours per month. So, we could actually look at an Uber interpretation here, if you would. Combining these two together. I could say on April 1st, 2011, in Joliet, Illinois, there was about 13.198 hours of daylight, and that number of hours of daylight was increasing at a rate of 0.993 hours per month. But I didn't. I wrote down the interpretation separately as indicated in the directions. So let's do one more example. Let's head on back and see what the example is, and then we'll come back and work it out on the chalkboard.
All right, we just saw an application of what was happening in Joliet, Illinois with the number of hours of daylight. And let's just look at one more example. This is kind of a classic example because it kind of goes back to physics. We aren't going to do a whole lot of physics in here, but I would be remiss if we didn't do at least just one physics example. So hey, there's this thing out there in physics called the position function. It's usually given by s of t, and the position function will give the distance an object is off the ground at a specific time t. And if you take the derivative of the position function, you get a new function called the velocity function. And the velocity function, it's nothing more than derivative of the position function, but it'll give you the velocity of an object at time t. So let's look at this example. The distance of raindrop which falls from a cloud that is 10,000 feet above the surface of the earth. So you got this cloud that's 10,000 feet above the surface of the earth, and a raindrop is falling from this cloud. Its distance is given by the position function. S of t equals 10,000 minus 16t squared. And t is measured in seconds, and S of t is measured in feet. Part A, determine the velocity function. That should be pretty straightforward. That's just the derivative of the position function. And then part B, compute S of 10 and V of 10 and interpret each. So if you need to write anything down, pause the video and write it down, because I'm heading off to the chalkboard to work out the solution here.
Okay, the last example, I mean, it's classic, you know, it goes into physics, very basic physics example. And it said that the distance a raindrop falls from a cloud that is 10,000 feet above the surface of the earth is given by this position function. S of t equals 10,000 minus 16t squared. T is time in seconds and S of t is in feet. So part A, determine the velocity function. Short and sweet here, folks. Velocity is the derivative of the position function. So if you get the derivative of the position function, that is the velocity function. So let's go ahead and get the derivative of the position function. Let's see, looks like sum and difference rule. The derivative of 10,000, 0. So all we have is the derivative of the second term, and thanks to the constant multiple rule, we get negative 30, helps if I write a 3, negative 32t. So that's the velocity function. Part B, we're supposed to find S of 10 and V of 10 and interpret each. Well, folks, you know I'm going to use the calculator here to get S of 10. So I put 10 in here for t, crank that through my calculator, and I get S of 10 is 8,400. What that means, t is 10, so that means 10 seconds after this raindrop has started to fall. Let me write that down. After 10 seconds, we know the raindrop is falling, so after 10 seconds it has fallen 8,400 feet. We were also supposed to evaluate and interpret V of 10. So I put 10 in here for t, and I get negative 320. Okay, so again, t is 10, so that tells me after 10 seconds, t is 10, after 10 seconds. Okay, now we have a negative 320. Now velocity, this is a derivative. It's a derivative. We need to see units. But the first thing I'm going to notice is this negative. That negative, that tells me the raindrop is falling. It'd be really odd if the raindrop didn't keep falling. But it tells me the raindrop is falling. So after 10 seconds, this raindrop is falling at a rate of 320. Now I need units. Well, since t was in seconds and S of t is in feet, the units would be feet per second. Okay, now negative. Then there's a negative sign here. No negative sign here. The negative is incorporated when we say it's falling. If you say something is falling at a negative, I don't know, what is that, double negative? It would be rising. We don't have to put the negative sign there. It's okay to say 320 feet per second. So that's it here in section 3.1, folks. Again, you know, read through the section. Hopefully you have been following along in the section. But read through the section, do the homework, and hopefully this material treats you well. That's it. Thanks for watching.